today I will talk about the dynamical system and how they can be applied to machine learning. There is the other part which is very, very interesting is how to apply machine learning to dynamical system. But today I will not have time to talk about that, okay? But I think that especially for our signal processing group, so what does our signal processing group study, right? They study dynamical system, they study time series, and actually they can apply machine learning to their study. Maybe I will mention about that very briefly. Okay, so what are dynamical systems, okay? So basically everything is a dynamic. Because dynamical system simply means mathematical theories to describe, to study things that move, that change with time, okay? So these are math theory, or models, if you like, for studying anything that move, that are not dead. So basically it's everything moves. So it means that we can apply dynamical system to the study of our universe, of our planets, of the small little things like the atoms, the elementary particles and things like that. And we can apply to the study of human, politics, etc. And of course to the brain. And when you talk about the brain, we talk about neural network. So neural networks are naturally dynamical systems, okay? Because the state changes. You can force the state to change. Then especially, I would like to mention here the things that can be, might be very useful for our signal processing group. So those are reinforcement learning, okay? I think that this will be useful for signal processing. And what they call fluid network, neural network, okay? This is a notion of architecture of neural networks called fluid. So I think that these things can be applied to, let's see, so we can use we can use dynamical systems to study things like, more mundane, like stock market, right? It's also a dynamical system, right? Etc. Like financial stuff. Let me follow my notes here. I have many notes here. And of course, we can apply our dynamical system to torus action. It's very important for us. Torus action is a dynamical system, so we want to predict what is the future of torus action. What is the energy, the stability, things like that. So all these notions of dynamical system can be applied to the study of outside our company. Okay, so basically everything can be modeled by dynamical systems. Is that okay? So in order to study dynamical system, we need to know, first of all, some very basic notions, and to have a good understanding of those notions, okay? Because they can be quite confusing, right? Those notions, we have to really distinguish the things, okay? So now I will talk about this really crash course about basic notion of dynamical system. Okay, so we have to really have a good understanding, or at least feel them somehow, okay, in order to be able to use it. So in dynamical system, in classical mechanics, okay, so people will talk about configuration and phase. Do you guys know about this was configuration space, phase space, or forget about confusion, position and state. Okay, so and these things are really different. So we have what is called state, and then we have what is called position or configuration, and those two things you should never confuse them. Okay, so for example, here is the position, okay? Or in general, configuration means that it is not only the position in the space, but also the orientation, okay? So you take the position plus the orientation. It is the configuration. Or if you study several objects together, like three-body problem, right? Or two-body problem, like husband and wife, you have two-body problem. So this is the configuration, okay? Now, the configuration space. So for example, so you look at the object in our, on the Earth, so you have a configuration which is basically three-dimensional. But if you use only three dimensions, three variables, you cannot describe the things that move on Earth using only configuration space. So what Newtonian mechanics tell you? So the Newton mechanics tell you that you have an equation like something like that. Right? So when you study the movement of something, you have to take not the first derivative, but the second derivative. Momentum. Okay? Now the first derivative is the speed or the momentum, and the second derivative is the acceleration. So actually the equation takes the second derivative, almost always, right? You look at all the physical books, the equations are almost always of second order. It is the natural thing in the physical world. The equations are naturally of second order. So it means that if you want to write it as an ordinary differential equation, you should write something like x and then v. Okay, v is the speed. Okay, and then you take the derivative, then it is become v here, and then it is fx here. So this is the ordinary differential equation that describe your dynamical system. Okay, now look. Here, x is a spatial variable, so it is the position, okay? But if you want to write the equation correctly, you need more variables. So you need not only x, but v, or the speed or the momentum, okay? The velocity of the momentum. And then it becomes a state. Is that clear? So the state is a thing that, with that you can describe your system completely. Okay? So if you write your system in state variables, or very often they call it phase variable, okay? So phase space. So then you have a Markovian system. It means that if you know the state at some point in time, you will be able to determine or to at least to infer somehow it is position in the future. So it is completely determined by it is state at one point in time, okay? So it is Markovian. Is that clear? It does not depend on the previous state. State is full information that you have already. But if you write something like this, you cannot infer the future state from just the position alone. Is that clear? And so this one, if you try to write a dynamical system using only configuration variable, it is not enough. Okay? So it is impossible, okay? So it is not Markovian. It is very important, this notion of Markovian, okay? Markovian means that you know something at some point in time, you know the future. Non-Markovian is that it is not enough, okay? Is that clear? Yeah. Okay, now, let me give you an example of a system which is not Markovian. It is the financial markets, okay? So when you look at like stock market, okay, you look just at the price of today, for example, then it is impossible to estimate, I don't know, okay, to the price of tomorrow, okay? Even if you add like noise, you add white noise, you add the volatility, etc., it is not true, okay? So the stock market, the stock price are not Markovian. So how to correct that problem? Right? You have to because in a system, when it is not Markovian, you cannot even calculate the distribution of tomorrow's price. It is not that you cannot calculate the tomorrow's price, you cannot even calculate the distribution of tomorrow's price based on today's price alone, because it is not Markovian. Okay, and in order to correct that, we have to, for the stock market, right, you have to introduce some hidden variable. So here in this case, for example, if you do not know V, then V is a hidden variable. Okay, and here consider X as a stock price. Okay, now you have to add hidden variable. It means that some momentum. Okay, the stock markets always have momentum. right? That's the first application. Is that clear? Have to distinguish between state and configuration. So another example, when we look at, for example, presidential elections, okay? So like Obama versus Clinton, right? You know, so at some point, Obama was very low. Clinton is like that. There's a number of people voting for her, right? In this, what they call this is a Democratic Party primary, okay? But the thing is that she was very high, Obama was very low, but the momentum are different. She had low momentum and Obama had very strong momentum, okay? So eventually, Obama overtook Hillary to become the presidential candidate of the party and became president, okay? So when we study things like politics, wars, economy, we should look not only at the current situation, but also the momentum. It's very important, okay? So this is the first notion, the distinction between state and position. So like right now, you have some position like you are data scientist, whatever. But what is your state? The state is not just your current position. It's also your potential of going somewhere, right? That's very important. And that is very often hidden. When people look at first at you, they do not see your potential. But when they work with you for a certain amount of time, they will see your trend. Okay. Now I try to move to the next page. Okay, I hope this was. So this is the first thing that I want to mention to you. Now, when we want to describe a system, we can use what is called a point. Okay, a point in a space. Okay, so basically you imagine that your space is like this, is the omega in your space, it can be phase space, and your point is here, you move from one point to another. So it is a point description, it is a geometrical description. Or you can use a function. Okay, so your state can be a point, or your space can be a function or a field. So, okay, so especially there's a notion of functions as state. So, I mean, in classical mechanics, usually a state is considered as a point in a finite dimensional space, okay? But in more complicated things like field theory or quantum mechanics, you cannot use the point as a state. You must use a function, okay? Because the state is so complicated that a point is, because the functional space is infinite dimensional, I mean, by definition, okay? So usually when the system is complicated, we need space of infinite dimension. So basically they are functional space, okay? So of course, when a point is also, when it is finite dimension, you can also use function, but function of a finite number of values, okay? So basically, this is a kind of duality between geometry and analysis. So people who know a bit about mathematics, you know this theorem of Genfan, right? Any topological space can be characterized by it is a ring of functions, actually, okay? This is a duality between analysis and geometry. Can describe things with points or with function. And so what does it mean? In dynamical system, we can describe the evolution of a system either by saying that, okay, we have these points that move, okay? Or we can say that it is the measures that move, okay? So it is the same thing in quantum mechanics. You know, there is two different formulations that are actually equivalent, okay? So either you can consider something as just constant, right? And the other things that move around it. So I am always young. It is the other guys, it is the world is getting old, not me, okay? It is I am constant, the other thing move. Or the world is the same and I move, okay? And actually these two different point of view that are dual to each other, but are the same, that both are valid, okay? So use points or use functions. Okay. So I mean, so all these ideas or different point of view might be useful when we study concrete problem or machine learning things, okay? Now, I move to the third point, which is very important. The notion of determinism and non-determinism. Okay. So in Newtonian mechanics, you have equation like whatever, right? This, and it is non-deterministic system. So it means that when you know the state at some point, and you are sure what will be the state at the next step. Okay, and here, but in our life, there's so many things that are noises, that are random. Okay, we call it random, and that we do not know, right? When the wind, we do not know, right? When we play ping pong, suddenly there's some wind. Okay, it is random. Okay, so we have to model those things, and they are basically mathematicians try to model non-deterministic things using what they call stochastic dynamical system. Okay, I will not go into the detail, but basically you will write something like, like you have an equation like z is a state, right? X is the position. So, but when you have state, deterministic means something like this. Okay, and no deterministic means something like you have something like this, but then plus some let's say some Gaussian, something, whatever. Okay, noise. Okay, some noise. Basically, they put white noise, Gaussian thing, because when we do not know about anything, we will assume that it is Gaussian. Okay, but it is not always the case. Okay, you cannot. Stochastic systems are very good model. Unfortunately, they cannot always be applied to non-deterministic system. Okay, there is another theory which is called random dynamical system. Okay, but I will not talk about it here. Now, okay, one important point: when the system are stochastic, so you see, this system is Markovian. Okay, when you go to a stochastic dynamical system like this, it is still Markovian. Okay, because when you know Z, you know the whole thing, but you know in terms of distribution. Okay, you do not know the exact position, but you have an equation that allow you to solve, and in a sense, okay, to know that there is a certain determinist. So the thing that will be determinist here is not the position or not the state, but the distribution of possible state. And we know the distribution will evolve with time. Okay, and that's the evolution of the distribution of possible state is a deterministic process actually. Okay. On the other hand, you can have random dynamical systems that are not Markovian. Okay, so it is important to distinguish between stochastic systems that are still Markovian and random systems that are very bad in the sense that they are not even Markovian. And their study is actually harder. And to study a non-Markovian system, one of the very important things, when I mentioned here already that when you lack variable, you have missing variable, like, right, then it is not Markovian. Right? You lack the momentum. So it means that you have some variables that are hidden. And so the notion of hidden variable is a very important notion in dynamical system. And of course, for neural networks. In neural networks, we have a lot of hidden layers, right? And conceptually, why you need hidden layers? I mean, even if everything is clear, is simple, you still want to have hidden layers, okay? Because hidden layers will give you hidden variables, and they are very important, because if you want to turn Markovian into something that is Markovian, it means that you have to add variables, and those variables are hidden. Okay, so a way to study non-Markovian, okay, system is to add hidden variable. Is that clear? Yeah. So they are conceptually important. Yeah? It is just not a mathematical trick. It is conceptually necessary.
Hidden random variables.
Yeah, stochastic random. But when you do not have inner variable, the system is not even Markovian. When you add some hidden variable, certainly you can turn it into, you can embed it into a Markovian system. Okay, and then you can use ideas from stochastic dynamical system. Okay. Okay, good. So the notion of hidden variables is a fundamental notion in dynamical system. Okay, and then we understand a bit better why in machine learning we want to have hidden variables. Okay, now the next notion is about integrability and non-integrability. Okay, yeah, integrability or solvability. Okay, and what is the opposite of integrability? It is a chaos. Okay. Actually, you can talk about regularity here. Okay. And it is chaos. Okay. So why we are called torus? Well, I can tell you that the torus is not a donut. Okay, okay, a donut is a very simplified, how to say, image of a torus. So, but actually, the torus means the best possible system. Okay, in the world, it means that it is a system which is really regular, integrable, stable, long time stability, etc. Okay, so okay, so so torus is here. Okay, and it is the rest of the world is here. Well, actually, you know about Henri Poincaré. Yeah, so Henri Poincaré was a very famous French mathematician who lived like more than a century ago, a bit more than a century ago, and he proved his very famous theorem that you take a three-body problem. It's a very like normal classical mechanics problem, which is three-body, and he proves that it is not integral in general. And then there are people like many other people that they prove that in most of the case, your system will contain something chaotic. So actually, you take a deterministic system, right? Take any deterministic system. Most of the time, it will turn out to be non-integrable and chaotic. Okay, so chaos. What does it mean to be chaotic? I mean, we will try to no. Okay, chaos is an abstract concept. Okay, but how do you determine? I mean, how do you prove or how do you decide that something is really chaotic? Okay, you need some measures, a way to measure it in order to show that it is really chaotic. Okay, so one of the way to show that it is chaotic is the notion called hyperbolicity. So if we can show that a system is hyperbolic, I mean, it is a really mathematical notion, okay? It means that some exponential, it's called Lyapunov exponential, exponents or whatever, and positive or greater than one or whatever, okay? This is a rigorous notion, okay? And if the system is hyperbolic, it will lead to chaos. And now, another way to show that it is chaotic is the notion of entropy, okay? So if you can show that the entropy is positive, then it is chaotic. Okay. Do you know the notion of entropy? So you know a guy called Shannon? I think he was Shannon. Okay. So Shannon is the father of communication, of information. Okay. So the story is that one day Shannon went and talked with von Neumann. You know von Neumann, John von. Von Neumann is one of the fathers of quantum mechanics and computers. Yeah, computing, and also game theory. And operator algebra, things like that. Yeah. And so Shannon showed to von Neumann, oh, I have this notion very interesting. I call it information. Okay, and then Shannon, and then von Neumann told Shannon that, oh, this is great. Your theory is great. This notion is great, but you should not call it information because that notion information already exists, so it confuses people. So you should call it entropy. So why entropy? Because first of all, because the notion, the word information is already taken. You have to take some other word, right? It is like trademark, brand name, right? Already taken. So why entropy? Because nobody knows what is entropy. So when you go into arguments with people, you will have an advantage because nobody knows what it is. So we have an advantage.
Maybe there's something appear before the name entropy.
Yes. So actually, in physics, it was a notion of entropy. So actually, it is a physical entropy, which was introduced by, I think this is in the thermodynamics, right? So people like Boltzmann, the guy who introduced entropy is, I think it was Boltzmann. Yeah, and then he went crazy because of that, because he was ridiculed by his colleagues. This guy is crazy. Why entropy? And so he committed suicide because of the entropy. Yeah. So actually, entropy is the quantity of information. Yeah. So that's the notion of Shannon. Okay. So you have absolute entropy or relative entropy. It means that when you add something, you have some more information in relative entropy. And then when we talk what is dynamical entropy, so I think the notion was introduced by Kolmogorov at first. Okay, you know Kolmogorov,
yeah.
One of the most important guys in 20th century mathematics. And so basically, entropy for dynamicals, it means that the rate of loss of information. So when you have a dynamical system like the quasar is a complicated system, right? You have to make measurements of, like Meteor France, right? They have like, things to measure things everywhere. So when I went somewhere for vacation, I also saw Meteor France, right? Like station for measuring things. And basically when you measure things, from your measure, you can predict the weather like for 1 week, 2 weeks. But after 1 week, 2 weeks, your measure become obsolete, become useless. Why? Because all those information that you measure now, in 2 weeks, they will lose their value, right? You cannot predict the weather for long term. You can predict long-term trends, maybe like, that summer is hotter than winter, but otherwise, what is the temperature like 3 weeks from now? Nobody knows, right? Why? Because we lose information. So the value of information is losing with the time, right? And so now when you measure, you always have things like the level of precision, right? So let's say you measure that it is here, but actually it is here, okay? So what is hyperbolicity? Hyperbolicity means that things diverge with time. So if you can measure something with, let's say, 1 millimeter precision, right? The level of information is very high. The level of information you have, or the quantity, is inversely proportional in a sense, okay, to the precision. Hyperbolicity means that when you have things that are first close to each other, so two states that are close to each other, okay, after some time they diverge, they go farther away to each other. And when things go, it goes exponentially. Like our company, when it grows exponentially. When some company collapse, it collapse really fast, like also exponentially. Okay, so it's supposed to have very small positive exponential in order to grow very fast. It is called the law of composite interest. It is one of the best law in economics, right? Like when you put your money somewhere and it makes it give you like 10% every year, right? Then you compose, and then after 30 years you become rich, right? It is the law of composite interest. And here the law of composite growth, right? If Taurus keep growing 30% a year, in 10 years will be really very, very big. And here the law of composite information loss. It means that at first you lose very little, but then afterwards you boom like this. It comes so far away. So you predict it is 30 degrees, but actually it becomes 45 degrees because it was just like that. Okay, so it is hyperbolicity. Hyperbolicity leads to chaos, leads to impossibility of long-term prediction. Okay, but something which is solvable, integral, is complete opposite. It means that we can predict the position of the moon 100,000 years from now with very high precision. Why? Because the solar system is very regular. It is a torus, okay? Toric system. That's why we can predict the position of the moon 100,000 years from now. Right? Yeah. When we talk about exponential, it is mostly Lyapunov exponent. Yeah. Okay. Now, just so many other notion, but I try. Okay, I try to quickly go to some other notion because they are all very fundamental, very important when we try to apply them to machine learning in particular. Okay. Now, there is this notion of equilibrium. Okay. So when we do like gradient descent method, what we try to find? We try to find some equilibrium point, like minimum point, right? You go to gradient descent, okay? So there is this, and it corresponds to the notion of equilibria in a dynamical system. Okay, when we talk about equilibrium, we want to talk about conversions. Yeah, how it converges to the equilibrium. Okay, and we will talk about stability. Okay, Lyapunov stability or whatever. Okay, okay, and those notions are related to gradient descent method. Okay, so when people invent gradient method, it is not something new. It is something that exists in dynamical system. Okay, now let's talk about stochastic equilibria. You know that when you do machine learning, then at each epoch you calculate your gradient. It is not the true gradient. It is a stochastic gradient based on the finite number of samples. And so, by definition, it is very stochastic. You don't even have the full state space. You have just samples of your space. You don't even know the distribution. Okay, you just guess the distribution, etc. So everything in machine learning is very stochastic. So it is natural to assume that machine learning is a stochastic dynamical system. And when we talk about stochastic dynamical system, what is the stochastic equilibrium? Okay, now I give you a very simple model. Okay, it is called damped stochastic oscillator. Okay, so oscillator is your pendulum, right? It's the pendulum, right? Oscillator, right? It goes around. But damped, it means that your pendulum, it loses energy, and then after some time it stops. Okay, slowly, but it stops. It is because of losing energy. Okay, but noisy. Okay, noisy. Okay, it means that from time to time you kick it a bit. Okay, and then and if you from time to time you kick it, you do not turn the thing, but you just kick the pendulum. Okay, and then it keeps going. Okay? Now, so actually the thing like this, if you have an equation like this, then it is the oscillator. Okay, and then if you have an equation like this, and then you add a noise here, it is a noisy oscillator. Okay, and then you add damping here. It means that you write like you make it lose energy. Okay, somehow. Okay. I cannot write a precise equation here. Then it is called damped. Now when you damp it, it loses energy. But actually, when you add noise, it will not go to zero. It will not go to zero. It will stay active. Okay? And there is a kind of stochastic equilibrium with positive energy. So a model like this will give you a kind of stochastic equilibrium with positive energy. Okay. Now the phenomenon is very interesting. When in the world we have this law of conservation of energy. Okay, the energy is transformed, not created, not lost. Okay, but in the real world we only have friction, we have damping, so things go down. But in the real world we also have noise. Okay, if you put noise together with damping, so actually there is a certain equilibrium level, positive energy, which is not lost. The energy is conserved. It's stochastic conservation of energy in the real world, where we have both damping and noise. So actually these two phenomena, somehow they in the stochastic world, but they cancel each other. So actually noise adds energy to the system. It is not true that when you have let's say a Hamiltonian system, you add noise. Actually, it does not make sense to talk about Hamiltonian noisy system. Why? Because by definition, Hamiltonian dynamics, most quantum and classical dynamics, they are Hamiltonian. The classical model of mechanics and physics, they are Hamiltonian. Okay, and by definition, they conserve energy. Okay, but actually, it does not make sense to talk about noisy Hamiltonian system. You know this guy Bismuth. He wrote a whole book about stochastic system. He has a chapter on Hamiltonian stochastic system. But when I saw it doesn't make sense. Okay, so actually, noisy Hamiltonian system, by his definition, actually it does not preserve energy. And when you do a reduction, it does not even preserve the symplectic structure. Okay, so actually you cannot do reduction with noisy Hamiltonian system. It does not preserve symplectic structure. Okay, now, but what is the implication for machine learning? So it means that because the system is always stochastic, you can never expect it to go to the minimum. It's impossible. It always go to some level which is higher than the minimum. Then this is the natural expectation is that when you train your system, it can never go to the true minimum. I mean, theoretically, you can never find it. It is not that your method is not good. Theoretically, you can never find it. Okay, it always go to some level higher than the minimum, and it's good enough. Okay, because by definition, your system is stochastic. Okay, so don't look for absolute minimum. Does not exist. I mean, in theory, it exists somewhere, but theoretically, you can never get there. Okay, now, okay, one more notion, and then I go to applications. Okay, and that's too many notions, but there's a notion of transformation. And then there's the notion of perturbation. I'm going to talk about transformation. So basically, you know about like Fourier transform, Laplace transform, whatever transform. Yeah, in mathematics, people invent so many different transforms. And what do those transformations do? Okay, so basically, you have a system like in a space like this, a system very complicated. I don't know, right? But then you make some transform. In another system, into another space, okay? And certainly the system behave very nice, okay? Be it Fourier, Laplace, whatever, okay? After the transformation, the behavior becomes nice. It is easier to calculate. And then you calculate here, the system look nicer, is simpler here. And after calculation, you can go back. The transfer should be somehow bijective in order to be able to go back, okay? And in mathematics, we have transformation, you have what is called normalization. The best normalization that you can have is a linearization, because you know when the system is linear, linearization. Okay, you can calculate everything explicitly. So the best thing you can have is linearization. Sometimes you cannot linearize. At least you can normalize. Okay. Machine learning. Okay, in machine learning, when you have an image, right, you want to say what is that, okay? You want to normalize the image, right? When you normalize, means the good size, good color, I don't know, good lighting condition, etc. Suddenly become easier to analyze. Okay, so that normalization step, it's an idea from dynamical step, very important for inference. Okay, in machine learning. Now, so I think that there's one last notion, okay? And then I have 10 more minutes to talk about machine learning. It's called reduction. And no, reduction, what does it mean, reduction? It means that you have a very complicated system, right? There's notion of micro-macro system, okay? System with an infinite number or a very large number of variables, right? Like Fred talked about the curves. Actually, the system of curves, it means the number of variables is very high. Or you have what they call fish blocks, etc. The number of variables is really high. Or economy, okay? And then you want to reduce the number of variables. So how you can reduce the variable, okay? Reduce the number of variables. When you want to reduce something in dynamic sense, you want to look at invariance, want to look at symmetry. Okay, and another method is called principal component. Okay, that Fred talked about. When you have invariance, you reduce the space. You take just a subspace, right? Because things remain invariant, subspace. When you have symmetry, you take the subspace and symmetry, you take the projection. It is different thing, okay? You take subspace or they call what they call the quotient space. Okay? Principal component, actually you cut it. Now, one thing, when you use principal component and you write your system using just the variable from principal component, the system is no longer Markovian. Okay, there is a reason for that. Because when you reduce the system, you want it to remain Markovian, you need these two things, either subspace or quotient space with respect to some invariance or symmetry. Okay, when you do principal component, you do not have symmetry. You kill the symmetry. Actually, the system is no longer Markovian. Okay? So it makes it more complicated. Okay, so I hope that you are not yet too confused with all these different notions. Okay, but all these notions, they are very basic in dynamical system, and they have direct interpretation in machine learning. Okay, so any questions before I go to machine learning? No question, Maria? Is that everything okay? Okay, good. Okay, so now I have here a list of 6 or 7 direct applications to machine learning. Okay. Some of them are already mentioned, right, during the first part. So, application. Sorry. Machine learning. So the first application is a so-called ResNet. You guys know ResNet? Residual network architecture. That actually we all use, right? I think that in every network that we use, there is this component called ResNet, okay? And what is the difference between ResNet and non-ResNet? Non-REST, okay? So REST for residual. Okay? So basically, you have a layer, let's say Z1, ZK plus 1, right? Some layer, okay? Equal to some operator applied to the previous layer, okay? That's the usual layer transformation, okay? Go from one layer to the next, apply some operator. That operator here may contain some variables that we learn, okay? Now, ResNet, you do not write this that way, but you write like this way. So, you know what is it is just a stupid invention, okay? ResNet, so it means that, now what is the difference here? The difference is that this guy here, now is this, okay? And this is the derivative. Okay, so actually a dynamical system, when you study dynamical, it is the derivatives that you study. Okay, and do you remember the theorem about the existent and unique set of solutions in dynamical system for ODE, right? For ODE. So the theorem basis on the fact that you can invert the operator. Okay, so this operator is always invertible, or it's locally. Okay, so it means that it's a bisection. This operator is not a bisection. I mean, in many cases, or even if it is a bisection, it is so bad because the eigenvalues are so small, right? So by doing this thing, you avoid what is called the non-bisectivity problem, the small denominator problem, okay? And certainly your computation become much easier, much clearer. It avoids what is called the vanishing gradient problem, okay? By adding this thing, the operator becomes identity plus something. Identity plus something small is only easily invertible. If it's not identity, this arbitrary operator, very easily you may fall into something which is very hard to invert. Okay? And then it will become really very difficult to compute. And that's why you will encounter those vanishing gradient problem. By simply adding this thing, you avoid vanishing gradient. It is always invertible. Okay, and this idea is actually the guys who invent ResNet, they were dynamicians. So this is the first very stupid application. Okay, the second application I already mentioned is that you do not expect the absolute minima. A good relative minima is okay. Okay, because by theory you cannot achieve absolute minima. The third application is that do you know why we use CNN, transformers, latent space? All those things have their ideas from the dynamical system. Okay, so do you know JPEG format? So the JPEG compression for image, they use wavelength. So JPEG format use wavelength compression. Okay, they do not use Fourier compression transformation. They do not use Laplace, Fourier, polynomial, whatever. Okay, why? Because when you want to approximate, because every single approximation you want to approximate, say, if you approximate them with Fourier polynomial, the approximation will require a lot of variables. Very bad approximation. But you use wavelength, certainly the approximation becomes easier with less variables, etc. Okay, higher precision. So that's why we always have to think about wavelength instead of Fourier. Fourier is forget what Fourier. Okay, always wavelength. So wavelength is a localized version of Fourier. Okay, and when we do CNN, we do convolution. Actually, when we do it right, convolution create wavelength. So convolution is not Fourier. Okay, it rather create wavelengths with those kernels. And it is a kind of when you transform it, it gives you information, etc. Okay, now quickly, why we do augmentation and normalization? No, so okay, so your space is like this, a space of unpossibility, and your space of normal form is like this. When you have some image, some data, some whatever here, or some state, you want to normalize it, means that you transform into something here. The normal state much smaller, much easier to study, and then you go back. Okay, that's the idea of normalization. The idea of augmentation is the opposite of normalization. It means that when you have some data here, you want to augment. It means that you want it to move away from normality. Okay, you want it to because you have few data. You want from the original data, you want to synthesize the data. You want it to cover as much space as possible. Okay? The opposite. So when you do training, you want to augment because you want to have a better distribution. Right? And augment to cover more space, better distribution. But when you want to infer, see, you want to normalize because in theory, normalized systems are much easier to study. It means that give you higher precision. Right? And the last thing, but it is a bonus, okay, that I want to mention is the notion of skin cancer. So what is skin cancer and why it is related to dynamical system? I mean cancer in general. What is cancer? Cancer is cows. Right? And what is cows? So cows is the things that grow wildly. Right? And so from the dynamical system point of view, it means that something that has high entropy. That has, so it means that when you, the basic idea is that when you have those known cancer, okay, and then the cancer one. So it means that basically it means that things that look so strange, so different from non-cancer, it should be cancer. Right? That's the basic idea. But of course we have to determine what is to decide what is non-cancer, right? And then from that, things that look too far away, too say. So that's why all those notion about asymmetry, too many colors. So all those signs that mean that they are too different from the non-cancer thing, right? That's the main idea. So it is the anomaly detection in general. Okay. So in general, when you detect anomaly, it means that you detect things with high entropy. Okay. That the notion of entropy is fundamental. Yeah. Right? The distance, the entropy distance in a sense, okay, is high. It means anomaly. It means cancer. Okay. So 55 minutes already. I will stop here. So thank you for your attention.